Hi there, Springboard Math Peeps. Welcome to Lesson 21.1, starting up in your book on page 357. So we've got one goal here today, and that's to create an exponential function to model compound interest. So we're going to create one after we learn how to do compound interest, and then we're going to use it to make some predictions and things. So let's get started. Madison received $10,000 in gift money when she graduated from college. She deposits the money into an account that pays 5% compound interest. So we're going to learn about what this means, but here's a definition here. Compound interest is interest or money paid by a bank to an account holder that is earned on both the initial account funds, so the amount you put in, which is also the principal, and previously earned interest. So it pays you interest on your principal and on your interest. So it keeps compounding. To find the total amount of money in her account after the first year, Madison must add the interest earned in the first year to the initial amount deposited. So we're going to find the interest for the first year by multiplying her deposit, $10,000, by her interest rate, 5%. So let's see. That's going to give us $500. So including the interest, how much money did Madison have in her account at the end of the first year? Well, she had 10,000 and she earned 500, so now she has 10,500. So the next year it's going to build on this amount instead of 10,000. So that's how compounding happens. So we want to record the amount of money she's going to have in her account at the end of each year. So we're going to complete the table and round the amounts to the nearest cent. So one way to do it is to take whatever the current amount is and multiply it by 0.05 to find 5% of it, and then add it back to itself. So we would get 500 here, and then we'd add it back to the 10,000, and that's what's going to give us 10,500. Then we multiply that by 0.05, and whatever we get, we could add it back to the 10,500, and then we'll get 11,025, and we could keep doing that. Another way to do it is to take the current amount and multiply it by 1.05, because what the 1 is going to do is it's going to give us the 11,025 that we already had, and then the 0.05 is going to give us the interest. So this is doing the multiplying and adding all in one step. So test it out. Make sure you understand that if you multiply 0.05 times 11,025, you'd get 551.25. Okay, so if you just multiply 0.05 times the 11,025, you're going to get 551.25. And then if you add that back on, you're going to get about 11,576.25. If I multiply this right here all together, then I'm going to get that whole amount altogether. So 11,025 times 1.05 is going to give me 576.25. So you can do it either way. Keep multiplying just 5% and adding it back on, or multiply by 1.05 all in one fell swoop, whichever way you feel more comfortable with and you really understand what you're getting. But you should make sure you're getting these amounts by yourself and not just writing down whatever I wrote, because that's not going to be helpful. Make sure you're rounding up if you need to for the nearest cent. So after 10 years, she would have $16,288.95 if all she ever did was put in this $10,000 to begin with and then left it sitting there. That's in a 5% account. Pretty cool, because the interest keeps getting figured on the previous principal and interest together. By the way, if you noticed in that previous slide that I rounded up one time incorrectly and ended up 1 cent higher than you, then you were right. So don't be erasing your stuff just because I said that. So the amount of money in the account increases by a constant growth factor each year. And we're supposed to identify that constant growth factor. Now I taught you how to do that before. You can always take 1 year's value and divide it by the previous year's, but I also just already sort of explained how to find that growth factor all at one time in the slide before this. So the growth factor was 1.05. It goes up 5% more than 1 whole. How is the interest rate on Madison's account related to the constant growth factor in item 3? Well, the 5% is added to 1, which represents the 1 whole amount. So the interest rate, which was 5%, is added to 1 in order to give the growth factor. All right, so now it wants us, instead of calculating the amount of money in the account after each year, we're going to write an expression for each amount of money using 10,000 and repeated multiplication of the constant factor. Then they want us to rewrite the expression using exponents. Well, I'll tell you what, they've showed us the 10,000, and then after the first year it would be 10,000 times that growth factor, and then on the second year it would be 10,000 times that growth factor, so all of that, whatever that is, times that growth factor again. And so that growth factor is squared. But this is going to get tedious real fast. So now we're going to have 10,000 times 1.05 times 1.05, and whatever all that is, we're going to multiply by 1.05. So that's the same thing as saying 10,000 times 1.05 cubed. I can't stand to do this part very many more times, so I'm just going to say this would be 10,000 times 1.05 to the 4th, and you can probably see the pattern then. 10,000 times 1.05 to the 5th, and on the 6th year it would be 10,000 times 1.05 to the 6th. So we're supposed to describe the relationship between the year number and the exponential expression. So notice the year and the exponential expression. And the year is the exponent. So the year is the exponent of the, what's that thing called right there that's got the exponent on it every time? That's the growth factor. That's the factor that's getting multiplied over and over and over. So then we're supposed to write an expression to represent the amount of money in the account at the end of year 8. So that would be our original principal amount, 10,000, times 1.05 for the growth factor, at 5% anyway, to the power of 8 for the 8th year. This is how you make money, people. By the way, in case you hear some sort of strange rumbling in the background, that's Kevin chewing on his bone. He's getting kind of crazy with it, so hopefully you can't hear it on my headset. But just in case, I didn't want you to think I was making some sort of weird sounds. Let's see, we're supposed to let t equal the number of years now, so we're going to use some variables. Express regularity, and we're going to write an expression to represent the amount of money in the account after t years. So it would be 10,000 for our initial amount times 1.05 to the power of t. T would be the number of years. And now we're going to evaluate that for t equals 6 to make sure we're right. So if we go 10,000 times 1.05 to the 6th, remember we have to do order of operations. So 1.05 to the 6th power is going to give us, please be doing this yourself, don't just copy down what I say, but it gives us 1.34. And so then when I multiply those, we're going to get 13,400. And then if we look back at our table, that should match. So if we look back at what we had after 6 years, it should be about 13,400. And if we figure it out for 10 years then, times 1.05 to the 10th, well, 1.05 to the 10th power, do it yourself, gives me approximately 10,000 times, oh gosh, I don't want to round this too much, so 1.628895, I guess. I don't want to round it too much until the end because it's more accurate if you don't. So if you leave the whole thing on your screen and don't round it at all, multiply it by 10,000, we're going to be off by a little bit. That's okay, because we're going to be approximate here as soon as we start rounding. So if I do it the way I rounded it, I'm going to get 16,288.95. Pretty darn close to what we had on our table. So we want to now write our expression as a function. So let's take all this information we got here and put it in function notation. M of t is the total amount of money in the account after t years. So M of t is going to be, for this scenario, a starting amount of 10,000 times a growth factor of 1.05 for that 5% to the power of t, t being the number of years. So I went ahead and graphed that function here. I want you to go ahead and get your points on your graph. Understand that if this is going from 5,000 to 10,000, then this must be about 7,500 here. And this must be like 12,500, 17,500, 22,500, like that. So get your points on there. Mine's not very smooth, but it should be roughly like that. And then so pause it, get yours done, and then come back to this. And describe the function as linear or nonlinear. Well, it's nonlinear. It's not an extreme curve on this scale, but we can tell that the rate of change is not constant. It's not the same between each consecutive term here. It's not always $500, so it's not linear. And to identify a reasonable domain and range here, okay, so here's the tricky part. The domain, that's the years, could go all the way from what? The lowest amount of years would be 0. That's when she made the deposit. And it can go infinitely. So x could be anything greater than or equal to 0. The range can keep going up. It's not going to go down. What is the lowest it could ever be? That starting value is 10,000, so it would be greater than or equal to 10,000. The years cannot be negative, and the amount cannot be below the principal deposit, the initial amount she put in. Madison's future plans include purchasing a home. She estimates she's going to need $20,000 for a down payment. And we want to determine the year she'll have enough money for the down payment. So she had $10,000 when she graduated from college, and we know she's earning 5% a year. We already know she has something over $16,000 on the 10th year, so I wouldn't check anything before 10. So we might try 11. This will just be a little trial and error to see when we finally have enough. So if we try 11 years, do it yourself. Let's make sure we agree. So 1.05 to the power of 11, leaving the whole thing on my screen, not rounding at all, and timesing that by 10,000, I get 17,103. So that's not quite high enough. So if I try it to the 12th power, let's see, 1.05 to the power of 12, I get 17.9, so not yet. So maybe I'm going to jump up to 15 and see if I pass it. So if I do 1.05 to the power of 15, you should be trying these things. Yeah, that's going to get me like 20,789. Can you see that? So I'm going to back up 1 year. That might do it, but I'm going to check 14 and see what that does. So to the power of 14, nope, I get 19,799, so that's too low. So it would take her the year, it would be 15 years, or year 15, when she'd have enough. And she'd actually have a little extra, a little more than she needed, but she wouldn't have enough in year 14, so we'd call it year 15. At the same time she opens her account, her friend Frank deposits $10,000 in an account with an annual compound interest rate of 6%. So we're going to write a new function for his account after T years. So Frank's is going to look like he's also, they have generous families that give him $10,000 when they graduate from college. His interest rate is 6%, so the growth factor is going to be 1.06. And it's going to depend on how many years. So we're supposed to predict how the graph of Frank's bank account balance will differ from the graph of Madison's. So what's going to be the same is that they start the same, right? But that's not what it asked us. So can you see that if his is growing at a rate of 6% and hers was 5%, that Frank's account will grow faster because it's at a higher rate. So his will be higher sooner. So now we're going to create a table for Frank's. And remember that the growth factor this time is 1.06. And read carefully because now we're supposed to round to the nearest dollar. And I don't know if you would have noticed that or if you would have just assumed we were rounding to the nearest cent like last time. So do it yourself and we'll hopefully make sure we agree. So I get 11,910, and then I get 12,625. Then I get 13,383. Then I get 14,186. And then I get 15,037. Then I get 15,939. Hopefully you're having a chance to stay ahead of me on this. Then I'd get 16,895. And then I'd get 17,909. So there's rounded to the nearest dollar. So if you put that on the same graph you had for the other one, then Frank's will look very similar at first, but then it's going to be this coming up a little bit higher here. So now it says at the same time that Madison and Frank open their accounts, another friend, Casey, opens a savings account in a different bank. Casey deposits $12,000 at an annual compound interest rate of 4%. So how does Casey's situation change the function? Write a new function, K of t, to represent Casey's account balance at any year t. I'm going to let you have a chance to pause it, try writing your own function. Let's see how it went. All right, so hopefully you came up with K of t would be 12,000 for starters, times, and her growth factor is going to be 1.04%. So, to the power of t. So Casey believes that since she'll start her account with more money than Madison or Frank, she'll always have more money in her account than either of them, even though her interest rate's lower. Is she correct? Well, you'll have to try some experimentation and justify your response using a table, a graph, or both. It might be easiest. You could easily smack her equation into GeoGebra and then make the viewing window match this scale and see how hers looks. See if it's gonna. She thinks that she will always have more money in her account. I know where these guys are after 10 years, so maybe it'd be easy for me to check Casey's after 10 years and see how it looks. So if I tried that, you do it how you want to, but let's make a good comparison here and see what we get. If I do it this way, 1.04 to the power of 10 gives me 1.48. So if I multiply that by 12,000, I'm going to get 17,762.93, which looks to be still a little bit maybe higher. So let's look at year 12 and see if that shows us anything clearer. So if I make this a 12, let's see what that's going to give me. 1.04 to the power of 12. Make sure you do your powers first. Times 12,000. I get 19 to 12 or so. And it's definitely higher than Madison's, but it looks like Frank's might be approaching something higher than 20 there. So what you might have to do is plug in something f of t for Frank's, something like 20 years, let's say. Well, his was 6% to 20 years, and Casey's was 12,000 times 4% in 20 years, and see what you come up with. I think what you'll find out is that Frank's and Madison's both. You could even do Madison's. After eventually theirs curve higher at a higher growth rate, so they're gonna pass. Oops, hers was 1.05 to the 20. They're gonna end up passing Casey's eventually. After 20 years, I'm getting 32,071 for Frank's and 26,293 for Casey's and 26,533 for Madison. So you can see both Madison and Frank are past Casey's after 20 years. So that's the magic of compound interest. And more important than amount, more important than principal amount, is time when it comes to growing your money. That's why it's more important to invest a small amount when you're young than it is to put $1 million in when you're 65. So 19 asks us, over a long period of time, does the initial deposit or the interest rate have a greater effect on the amount of money in an account that is interest compounded yearly? Well, we sort of already noticed that the rate has a bigger effect because now this is all based on a long period of time. On a short period of time, the initial deposit will be higher, but the interest rate that's higher will have the biggest effect because it causes, well, if we looked at a graph, let's say, the graph to curve more steeply, which means it's increasing faster. So the interest rate that's higher will increase faster. So now, this next part, I guess I'll read it because it's here, but you should read it yourself, and it might take more than one time reading through it to soak in what it's saying. But most savings institutions offer compounding intervals other than annual for compounding. And for example, a bank that offers quarterly compounding computes interest on an account every quarter instead of just every year. That is, at the end of every 3 months. Instead of computing the interest once a year, interest is computed 4 times each year if it's done quarterly. If a bank advertises that it's offering 8% interest compounded quarterly, 8% is not the actual growth factor. Instead, the bank will use 8% divided by 4, which is 2%, to determine the quarterly growth factor. What is the quarterly interest rate for an account with an annual interest rate of 5%, compounded quarterly? Well, we'll take our 5 and divide it by 4, and we'll get 1.25 for our new percent. So that's going to be the interest rate for an account that has an annual interest rate of 5% that's compounded quarterly. So the quarterly interest rate will be 1.25%. Interest can be compounded semi-annually, which means twice a year, every 6 months, quarterly, every 3 months, monthly, and daily. There's all kinds of varieties. All right, so we're going to suppose that Madison invested her $10,000 in that account described in item 20. So in item 20, remember she was getting 5% quarterly, so the quarterly rate was 1.25%. Now be careful when you do the growth factor. 1.25% is not 1.25 growth factor. 0.0125 would be the percent part, right? Because you move this decimal 2 places. So 0.0125 is the percent. And then remember, you can either multiply that to the previous amount and then add it on, or you can use the 1 for the whole. So the growth factor would be 1.0125. So keep that in mind for this growth factor of 1.25%. So if we're doing this quarterly, after 3 months it's going to have 1 compound. 6 months will give it 2 compoundings. 9 months would be the 3rd, and then the 12th month, or 1 year, would be the 4th compounding. In 4 years, it compounds 4 times per year, so that would give you 16 compoundings. And in T years, that would give you 4, because there's 4 quarters times however many years. So if we want to do the account balance, we're going to take our original 10,000, and then for this first year, we can multiply it by 1.0125 growth rate. So make sure you understand where all these pieces are coming from. And we'll end up with 10,125. And then I can just keep using that growth rate as long as we're going by 1 compounding at a time. So the next compounding would give us 10,252. And the next one would give us 10,380. And the next one would give us 10,509. And then I can't really keep multiplying just by that 1 growth factor. So what I'll have to do is probably set up a a function here or an expression. So 10,000 times 1.0125 to the 16th power for this 16th compounding period. So do that yourself. We'll see if we agree. 1.0125 to the power of 16, and then take that and multiply it by 10,000, and you should get something like 12,199 if we're going to the nearest dollar. So then for this compounding period, we'd have to think of it as this initial amount times 1.0125 to the power of 4t. And that'll be able to tell us for any given number of years. So we just sort of did this. A to the t equals, so if it's compounding 5% a year, compounding quarterly, we took our 5%, divided it by 4, and got 1.25% for the quarterly interest rate. So that means our initial amount, our principal, times a quarterly growth rate of 1.0125, because remember, this would be 0.0125, and then we also have to add that to the one before it, so the one whole, and then the 1.25. So this is basically 100% is the whole one, so that's the amount you had, and then 1.25%. So 1.0125 growth factor to the power of 4t, because for any given number of t years, it's going to compound quarterly or 4 times a year. So for 20 years, we would have A of 20 would be 10,000 times the growth factor to the power of 4 times 20, which is going to compound 80 times. So 10,000 times 1.0125 to the 80th power. So let's do it and see if we agree. To the power of 80, and then times 10,000, and I'm getting $27,015. See if, whoa, and then I crossed it right out. $27,015. See if that's about what you're getting. Okay. All right, so here is kind of a summary of what we're going to be doing here, and I would encourage you to read that several times, 100 times if you need to, until it kind of soaks in and you can see that that's what we're doing here and why we're doing it. But for the compounding periods given below, this is going to be a great little summary for you to see how to work all the different compounding periods. We're going to write a function to represent the balance after t years in Madison's account, and then we're going to calculate the balance after 20 years. So she is investing 10,000 at a rate of 5% annual compound interest. So yearly, that's going to look like 10,000 times 1.05, because there's the 5%, okay, but the growth factor is 1 plus the interest rate, so 1.05 to the power of t. So for 20 years, it's going to look like 10,000 times 1.05 to the 20th power. You should do it yourself. You should set these up yourself and then look at this. You shouldn't even be copying down the setups, because that's the most important thing for you to be able to do. So if I do 1.05 to the power of 20 and then multiply that by 10,000, I'm going to get 26. Let's see. I'm just going to round it to the nearest dollar. It doesn't tell me not to. 533. All right, so we're going to have to think here for quarterly, right? We're going to start with our same 10,000. If we're writing a function, I guess it would be M of t, Madison's account value, or A of t, account value maybe. So this would be A of t equals 10,000 times, now quarterly, remember we're going to take the 5 and divide it by 4, so we get the 1.25. So it's going to be 1.0125 because it's this percent in decimal form, which would be 0.0125 plus 1, so 1.0125. And it's going to be to the 4t, because that's 4 compoundings per year. So this would be 10,000 times 1.0125 to the 80, and that's going to give us, do it yourself, hopefully you're setting the whole thing up, 0125 to the power of 80 equals this, times 10,000 equals 27,015. Now monthly, so the amount is going to equal 10,000 times, now 5% divided by 12 months a year, right, is going to give us an interest rate of 0.42. So the growth factor will be 1.0042. And it's going to have to be to the 12t, because this monthly means it's going to compound 12 times a year. So that'll give us 10,000 times 1.0042 to the 12 times 20, which is 240th power. So do that one. So you get 1.0042 to the power of 240 times 10,000, and you get 27,343, let's say. Then daily, all right, now we're getting fancy. So the amount is going to be 10,000. Now, daily is going to be, let's see, maybe I'll come over here so I've got room. 5% divided by 365 days in a year, right? So that's going to give us 0.01, maybe I'll call it 0.01, I don't know how far to go. I guess I'll just round up 0.014. So times a growth factor of 1 point, now we've got to move this decimal 2 places, so 0.00014 to the power of 365t. Okay, that's going to be fun. So 10,000, this is going to be huge, power, times 1.00014 to the power of, I don't even know what 365 times 20 is. 365 times 20 is the power of the 7,300th power. So 1.00014 to the power of 7,300 times 10,000. And we get something like 27,785. So there's our values, compounded daily, monthly, quarterly, and annually. So then the question is, what is the effect of the compounding period on the amount of money in the account after 20 years as the number of times the interest is compounded each year increases? So the more compoundings per year, or aka the shorter the compounding period is, so if it's 3 months or 1 day, whichever one's shorter, that means it'll be compounding more times. So the more compounding periods, or the shorter the compounding, the more the compoundings, because the shorter compounding period, the more the account will grow. So you better process that, because I said that pretty badly. See if it makes sense. And everything on this page is going to take you some time, but I cannot stress how important it is to get it mastered for yourself. So we'll go over anything you need to go over, but just I don't think it's too hard for you. You be sure to ask. Just make sure you've taken the time to understand where how all of the decimals moved, how you found all of the growth factors, how to turn percents into decimals, and so on. So we'll see you in class.